transistor. Now the operation. So whenever I told you, whenever you are going to use a depletion MOSFET, you are going to apply negative voltage to gate. So whenever I'm going to apply negative voltage to gate, it will attract the free electron in the channel to the metal surface. So this reduces the number of carriers in the channel. So whenever I'm going to apply negative voltage to gate, in the channel I'll be having equal and opposite charge. So I'll be having more number of holes in the channel, which will reduce the number of majority carriers. Okay, due to reduction of majority carrier, drain current is reduced for increasing values of negative voltage in the gate terminal. So whenever because of an applied voltage something is reducing, that is going to be depletion MOSFET. You know, in N-type electrons are majority carriers. By applying negative voltage at the gate terminal, you are going to induce more positive charge in the channel. So when more positive charge is induced in the channel, the majority carriers are reduced in number, giving rise to reduced drain current. When you increase the negative voltage VGS applied, the drain current keeps on reducing again and again. This is the depletion MOSFET. If you are going to go for enhancement operation, you have to give positive voltage to the gate terminal. When you give positive voltage to the gate terminal, negative charges will be induced inside the channel. Channel already has lot of electrons. Now we are inducing new electrons also. So more electrons will result in more drain current. So for depletion MOSFET, the drain current will reduce as you decrease VGS. For enhancement MOSFET, your drain current will increase as you increase the VGS. So you can see the graph here. It's very clear. So when VGS is 0, you have a minimum drain current. When you increase VGS in positive direction, you can see that the drain current is increasing. But same case, when you increase VGS negatively, 0, minus half, or minus 1, you can see reduction in drain current. So this enhancement type or the depletion type fabrication is same. Only thing, how we are going to, what voltage we are going to apply to the device to make it enhancement or depletion type. Generally, when you give negative voltage to your device, it acts like a depletion MESFET or MOSFET. So in the reverse, if you apply positive voltage to the gate terminal, it is going to work like an enhancement MOSFET. So this is the characteristics for both income, the drain characteristics for both the MESFET combined. So when positive value of VGS, it is going to be enhancement MOSFET. For negative value of VGS, it is going to be depletion MOSFET. And the fabrication, everything is again same. For this is going to be enhancement type MOSFET. And I'm not going to have any special channel between the, because this is fully N-type channel only, right? So I'm not going to have a specific channel here because already I have an N-type channel and I'm going to increase the number of electrons. So there is no need for a separate channel between the source and drain for enhancement type MOSFET. And here you can see this dark line is missing. This dark line, if it is there, it is going to be depletion. The dark line is missing, it is going to be enhancement type MESFET. Okay, but due to the Schottky barrier at the gate, the positive threshold voltage is limited to 0 volt to about 0.4 volt because turn-off voltage is about 0.7. So even though you are going to have a Schottky barrier, the device will work only after 0.7. 0.7 is going to be, you can say it is the turn-on voltage for the barrier diode. So only after 0.7 volts, your device starts conducting. Before 0.7, the output will not be, output will be 0, or I can say the current is going to be 0. So when a positive voltage is applied, channel is created, which will result in large number of electrons. So the schematic for N-channel enhancement MOSFET is given. See here, this is the diagram for N-channel MOSFET. Only thing, if you see, for this is N-channel enhancement MOSFET, MESFET, and for depletion, you see the difference is you have a thick shading here for depletion, and which indicates the channel. Here, but enhancement MOSFET channel illa, so it's going to be blank. That is how the diagram is, the notation of the MESFET is drawn from the diagram, from the fabricated structure of your enhancement type MESFET. As the mobility of holes is very, very low compared to high charged electrons, you don't prefer holes are not preferred for high speed communication because they will make your device slower and slower. So depletion, the Same construction is followed for enhancement and depletion, resulting in commercial availability of N-type gallium arsenide MESFET. The N-type you have enhancement and depletion. Same way in P-type also you can have enhancement and depletion, but that's what I have said. In P-type, the holes are the majority carriers, and mobility of holes, the velocity of holes, everything is very very small compared to electrons. So you don't prefer P-type devices being fabricated. So N-type like depending on the voltage what type is applying to VGS, it can be enhancement or depletion type MESFET. And the length of the channel is made very, very small for high speed application. That's what we have seen in MESFET. The gate length is 0.5 mm. So as you go for a HEMT and HPT, we have seen the gate length is reducing. So gate length or the length of the channel is very, very key parameter to understand the possibility of using MESFET for high speed applications. So, and also think the key in MESFET, there is a high mobility of electrons compared to MOSFET. So when you compare MESFET and MOSFET, the electron mobility is very, very high in MESFET when compared to MOSFET. Okay, because the depletion region is separates the carriers from the surface, the mobility is close to that of the bulk material. So high mobility can lead to high values of current and transit frequency. So when the current is going to be very, very high, when the gate length is going to be very, very small, the transit time is less. So the operating frequency will be very, very high. So MESFETs can operate at a very high frequency compared to MOSFET. And MOSFET with a MESFET, the electron mobility is very high, which makes it a high frequency device. Only disadvantage is presence of metal semiconductor junction, because you have to wait till zero point 0.7 volt for the device to conduct. The same thing happens in PN junction diode also, right? So you have to wait for 0.2 volt for germanium and 0.7 volt for silicon for conducting. Same thing here also. So even though the device is fabricated using gallium arsenide technology, since you have a metal semiconductor junction, that junction will be turned on only after only above 0.7 volt. Okay, the typical turn on voltage is 0.7 volt for gallium arsenide Schottky diodes. So the threshold voltage must be lower than its turn on voltage. So you cannot wait for the device to turn on a very after a very long time. That is going to make your device very, very slow, right? So that is the only issue we are facing with the gallium arsenide MESFET is reducing the turn-on voltage. Threshold voltage is fixed for a device. You cannot modify that, but turn-on voltage is going to be what you can, by fabricating the proper metal semiconductor junction, I can modify the turn-on voltage accordingly. Okay, and whenever you are going to have a large number of enhancement type of MESFET, it is becomes very difficult to fabricate, because the technology is very, very delicate. So even a small mistake you do, the problem, the device will not be fabricated properly. So you have to be very, very, very careful while fabricating MESFET.